was originally at MIT. He did his bachelor's and master's from MIT, so welcome back. Then he decided to take a trip across the coast in beautiful Berkeley, where he has been working with Peter Bartlett and Mike Jordan. So he has worked on a bunch of topics concerning bandits, reinforcement learning, and so on. And he's been doing good theory of these topics as well as application. So very excited to hear from you, Aldo. The floor is all yours.
Thank you. Thanks a lot. So as Cookie mentioned, I'm here at Berkeley, co-advised by Peter and Mike, Peter Bartlett and Mike Jordan, and I'm interested in a bunch of things, ranging from reinforcement learning to online learning bandits, and both from a theory and a more applied perspective. So today's talk is going to be a little bit more applied in nature. So just kind of to put it out there. So let me start. So today I'll talk about some recent work with some collaborators. There are 3 papers, or 2 papers and 1 small workshop paper woven into the talk. So what we're trying to do here, or I'm trying to do here, is to explore how to use policy representations and how to use them to guide learning in reinforcement learning. As I mentioned before, this is your work with great collaborators, including Jack, Christoph, Junghao, Anna, Mike, Steven, and Robert Miller. Okay, so let me start. So what I'll talk about today, so I'll start by giving you a brief intro to RL, for those that may not be familiar with it. And then I'll try to answer 4 questions. Basically, the first thing I'll talk about is the following thing, which is what is the right measure of similarity between 2 policies. And then I'll try to answer that question by giving you some ideas on how can we possibly answer this question in a meaningful way, and how the answer will lead us to get to some algorithms that leverage the solution, I guess, quote unquote, to do a bunch of different RL type, solves a bunch of different RL types of problems. And then we'll look at how can we use this framework of thinking to design algorithms, a particular algorithm in this case, to effectively encourage diversity in a population of RL agents. And then I'll finish by touching on the following sort of meta question, which is what is the right measurement similarity between tasks that should tie with the previous discussion, sort of in a progressively more complex way. Okay, so let's start with MARKOV decision processes. So the key difference between reinforcement learning and other paradigms in machine learning is the sequential nature of the reinforcement learning problem. When we talk about reinforcement learning, we typically focus on solutions to final MARKOV decision processes, or MDPs. So now MDPs are a framing of the learning from interaction problem where, as we have in this picture, an agent begins at a particular state, and then takes actions until some termination criteria, such as, for example, running out of time. So the agent performs some actions in an environment, receives a reward, and then moves to different states where it performs new actions and so on and so forth. So the objective of the reinforcement learning problem here of an agent in this sort of paradigm is to maximize your reward. There are multiple ways in which you can sort of state this. You can state this in an episodic setting where you do not do any discounting. You stop the agent at a pre-specified number of steps, and you're trying to find a policy, which is the mapping from states to actions, that allows the agent to maximize the expected reward collected. There's also the discounted setting. So in this chat and these applications as well, we'll mostly use just the undiscounted formulation, so episodic. Okay, so here are some notations I'll use throughout the slides. So when I talk about, I may not use them too much, but still they're there. So the first thing is an MDP, so we usually denote it as a tuple. made up of a state space, an action space, or an action set, the transition dynamics, which is denoted as P here, and then the reward function. The reward function here is thought of, as, you get a sort of random reward when you choose a random variable, but it's the mean of the reward depends on the state and action of state and action pair where you have executed such where the agent may be and the action that the agent may have taken. And as I described before, a policy here is just a mapping. Throughout the discussion, there'll be policies parameterized by some parameter, which I'll denote as theta here. And it's a mapping from states to actions, parameterized by theta. And something important here that I'll introduce, that sometimes we don't talk about too much, is the space of trajectories. So a trajectory is just a concatenation of what happened in interaction between an agent and the environment, or the MDP, and it can be written as I mentioned there. So there are these huge tuples that contain states, actions, rewards, and the trace of interaction of the agent with the environment. And so in this case, if you think of it this way, a reward can be thought of as a function from the state of the reward collected throughout a whole trajectory. Can be thought of, in this case, undiscounted, episodic, as the sum of the rewards along the trajectory. So as a function from the trajectory space to the reals. And so if you think it that way, then the objective here is to find a policy that will maximize the expected reward function as seen as a function from trajectories, sampled from the policy distribution over trajectories to the reals. Okay, so next thing is what's the objective, as I mentioned already. You can think of it as this function. Sorry, I use my hands a lot, but so then I'm just pointing to the screen, so sorry for that. So we have the following objective usually, which is you have a reward that, as I mentioned before, we'll think of it as a function from trajectories to the reals. And what we want to do here is to find a policy parameterized by theta that maximizes this expected objective. So a way to do this is using, for example, policy gradients. Vanilla policy gradient algorithms, what they do is they take gradients that look in the following way. So you take gradients of this precise objective function, which then you can write in this more compact form that is very convenient, because then you can take actually trajectories and use those trajectories to compute unbiased gradients. Stochastic gradients are unbiased, so then you can take gradients using that. So that's nice. So also, oftentimes this is done not just by taking gradients as in the previous slide, so just simply taking these unbiased samples of trajectories and taking gradients, but using a cross region type of method. The kind of constraint in the how much you move in parameter space is oftentimes done using a KL type of count, which is abbreviated in this way. So usually methods for cross-region policy optimization, what they do something like this, which is taking a step at every time step that maximizes the local, approximation of the reward function, of the expected value function, subject to some KL constraint. So here is how you would do optimize something like this. This is kind of this is all a review, let's say. Okay, and then another method that is common, again, is all in practice, for doing policy optimization is the following strategy, which is called evolution strategies. The name in the part of the name that says evolution here is a little bit misleading, I would say, because when you look at the method, it actually really is more a sort of randomized finite differences type of method that smooths out the function that is optimizing, treated as a black box function in this case, and then takes a stochastic gradient with respect to that smoothed version of the function. So here, basically, the main takeaway is that what we do here is we forget. So what, not we, but what people do when they use evolution strategies is to forget completely the structure behind the function and just treat it as a black box. Meaning, so in this case, we want to maximize the expected reward of a policy parameterized by a parameter theta. So we would treat this as just a function from thetas to the expected rewards. And then we will use this sort of black box method to optimize. And then I think this is the last sort of background thing that I need to introduce. So there's another method that is very related to a method that uses evolution strategies as part of its how it works. That is called novelty search. That will use, I guess, with my colleagues in some experiments here when we show some plots. So this method is an extension of evolution strategies, and the idea is it tries to boost exploration by adding a term that you can see in this on the slide. So instead of just optimizing for the reward, we also add a novelty type of term, so which measures the distance of the current point, so the current new policy that we may be proposing with respect to the previous one. So trying to encourage novelty, hence the name. The extra bit of diversity that is added is called the behavioral characterization, which is trying to encourage the policy right now to be different from what has happened so far. Okay, so this sort of brings us, after this small introduction, this brings us to the first question that we mentioned we would treat here. So, which is following. Okay, so what is the right measure of similarity between two policies? Okay, this is a bit of a not very well formed question in a sense right now, but I'll tell you more what I mean by this. Okay, so the sort of working hypothesis or working observation here is the following. So two policies may perform very different actions at a local level, but actually may result in very similar global behaviors. So here there is a small drawing here. So you have two trajectories in this case, but let's say these are two grid worlds that are deterministic. And on the left, we have, the first agent is trying to both, in this world, the goal is to go from the beginning to the purple state, from the start state to the purple state, but while avoiding the lava spots. So if you look at the left trajectory, or the left trajectory, you see that this agent managed to not die on the lava spots and then reach the goal. And the same happened on the right side. But if you look at very fine grain, so like a very local level, these two solutions are very, very different, but they actually have the same goal, which was precisely that it avoided the lava and reached the goal. So we want to kind of try to formalize this a little bit more and try to use some of the intuition from this to try to come up with signals that can guide algorithms for doing some policy optimization or some other tasks in reinforcement learning. So let's see another example. So two policies may perform similar actions at a local level. So they may also look very similar locally, but they could also be very different at a global level. So this is not going to be a grid world example. It's going to be maybe more interesting. Actually, not more interesting, but more fun. So let's say you have two cars, just kind of a more like real world thing. So let's say you have car one, car two. Both are an SUV. You have black in color of the cars, the same year. Sorry. Yeah, so they have the same mileage and like same gearbox. So they look very similar, right? Like if you look at these features so far. But it turns out that car one is, let me remember what type of car is this. It's basically a cheap car. Car one is a Vauxhall Crossland, yours for over 12,000 pounds. And then the second car is actually is a Lamborghini. So it's a little bit more expensive. And you can see here, oh, sorry, something happened with the bar below. Okay, good. You can see here that, well, basically in the thing that matters perhaps here, which is, you know, the acceleration and the price, they are quite different. Okay, this was a bit of a stretch, I know, but I hope this makes some sense. Like, you can have policies that are looking very similar in a sort of local level, but actually they result in very different behaviors at the end that are very distinct. Okay, so how do we try to make use of these ideas, right? So first thing is, I'm going to introduce the idea that a policy, this induces a distribution over trajectories. I mean, this is not a new idea, but this is kind of a way of thinking about policies. A policy has like a bunch of trajectories, but not just actually a bunch of trajectories, actually a distribution over them. So which will denote P of pi whenever we say policy pi induces a distribution over trajectories. So that's P pi. Okay. So how do we use this to define a behavior? The idea here is the following. So we have what we call behavioral policy embeddings. So these are, we distinguish two classes: on policy embeddings and off policy embeddings. So the behavioral policy embedding is just a summary of a policy's behavior. You look at a trajectory, and this will define what the trajectory did, or like what's the behavior that this trajectory is encoding. So that's the case in on-policy embeddings, and for off-policy embeddings, which also come in our algorithms, what we look at like is at what policies, what the actions of a policy do over a state probe distribution. So here, a little bit more in detail, what we mean by on-policy embeddings. So we have an embedding map, which is this curly E, which maps trajectories to an embedding, to a summary of a trajectory. In our experiments, we experiment with a few types of embedding spaces or embedding maps. So for example, a state-based embedding map based on the last state that the trajectory saw, an action-based embedding map that corresponds to all the actions that the policy has seen in a trajectory, or the reward-based one, which is just the reward collected by a particular trajectory. So here, the reward one, let me tell you a bit more about it. So if you think about two trajectories, there is a natural order in between them, which corresponds to how much reward did they collect. And so even if two trajectories are very different in its like which states they visited, which actions they took, if they collect the same reward, they in a sense should be treated similarly. So that's kind of the intuition of why that particular type of summary or embedding makes some sense. Okay, and so then the idea here is what we'll do is we'll use these embeddings to compare, we'll think of these embeddings as like a way to compare trajectories in the space where it matters. Okay, and then crucially, what we also have is we assume that the embedding space is equipped with a cost function or a distance metric that allows us to compare summaries of trajectories in that rightful space. So for example, in the case of a reward-based embedding, you have like differences of rewards. They correspond to like meaningful distances between embeddings. Or same in the state space, if we have something about the space that we know. Okay, and for off-policy embeddings, what we'll use is a state probe distribution, a policy, and then just the actions or the distributional actions that the policy that we are trying to evaluate executes over those that probing probing distribution. And examples of probing distributions could be, we look at previous policies or an ensemble of previous policies that we have encountered throughout optimization, or let's say a bunch of states from the data buffer. Okay, so to get more in like more concrete, how are we going to use these signals that we are sort of alluding to is through what we call through a Wasserstein distance. So remember that we think of policies here as distributions over trajectories, and actually not just that, but distributions over embeddings. So because we said that in the embedding space we'll assume the existence of a cost function, or distance, then it's natural to think of comparing these distributions over embeddings using a Wasserstein metric. And then for the purpose of making things tractable and like usable for our algorithms, what we actually use is the smoothed version of the Wasserstein. Okay, so the Wasserstein distance in this case is the following. So if we have two distributions and a cost function between pairs of elements in the domain of one and the other, the definition of the Wasserstein distance is just this optimization problem, which is the minimum overcouplings of these pairs of samples from the two distributions of the expected cost of transporting one to the other. So in our case, what we'll do is we'll also add this regularizer, which is a KL with respect to a fixed distribution, because what this allows us is to go into the dual formulation, which is the same as the primal here, but it'll allow us to actually take stochastic gradients through it. So what we actually do is we'll think of the Wasserstein distance between two policies here in embeddings of trajectories. You should think of it that way. As actually trying to solve, whenever we say we want to compute that kind of distance, it means we want to kind of compute this, the dual formulation of it. So we'll call the lambdas that appear here in the dual formulation, the dual test functions. We'll refer them as test functions, behavioral test functions, to add more lingo to this. And then basically what happens is the second term in the dual formulation allows for gradients. So one thing I want to say about the test functions is that they basically capture the relevant regions for each of the distributions. So this will actually allow us, and you'll see in the next slides, to get a signal that we can add to the reward basically over trajectories that can encourage optimization of encourage our policies or our algorithms to lead the policies that we are optimizing towards or away desired or undesired behaviors. Okay, so a little bit more intuition here. So in the case of one policy embeddings, the idea is this. So the Wasserstein distance between two policies using the embedding space and the metric in the embedding space can be, roughly speaking, and this is kind of an approximation, written as this difference of expectations over the test functions. So now the nice thing here is that these are actually on policy objectives. So this distance can be, roughly speaking, again, written as this difference of expectations, but now with respect to the policies that we are trying to evaluate the distance of. For off-policy embeddings, the story is a little bit different, but similar in the sense that like what happens is we get expectations over probing distributions for the policies that we want to compare under this distance. So what I'm talking about right now is like how to compute or how to interpret a distance, this Wasserstein distance between two policies once we have some embedding of trajectories or these off-policy type of embeddings, and we want to compare them using them. Okay, so but I guess the point, the thing we want to actually get at is like how do we use this notion of a distance to, I guess, to build better algorithms for reinforcement learning? How do we leverage this information for RL? And this is the topic, sorry. Yeah.
Can I ask a question before you
Yeah.
move? So how do you find the embedding phi?
Oh, yeah. So right now, this is like, right now we define the embedding to be a bunch of different things that we think could be useful. But ideally, you would want to actually kind of learn the embedding itself. We haven't done that. So that's kind of a very good question. But see, yeah, so right now throughout this talk, the embeddings are basically chosen. But nothing is preventing us from, I guess, trying to actually learn them as well, except potential computational and time, but yeah.
Okay, and is there some criteria for choosing the embeddings, or is it task specific?
So, right, so what we tested here were like these very generic things, like for example, the last state or concatenations of states. I mean, things that are not necessarily task specific, but I'll show you an example where a task specific thing makes a lot of sense and like gives you some. So I mean, it's kind of a combination of both. We tested like non-task specific things in some of the experiments, but like task specific stuff can probably help if you know something about the semantics of the task.
Okay.
Okay. So yeah, so now let me show you how we use these definitions of distances to get some signal to do policy optimization. Okay, so basically the idea is we're going to use these signals, the test functions that are given by the Wasserstein distance, to score behaviors. So, and basically the main building block of the algorithms that we'll propose will be this following Wasserstein regularized objective, which takes this form. It's made out of the reward signal. This is not necessary, but some of the algorithms we propose look like this. So you have the reward signal, and then you have a regularizer that corresponds to a Wasserstein distance with respect to some base distribution, which could be, and then a regularizer beta, which could be positive or negative, depending on if you want to be close to the reference distribution or embeddings, or to be far away from it, to encourage like exploration, for example. And here you see how the objective translates into a gradient for both on-policy and off-policy embeddings. In the case of on-policy, the objective, as we said, and using the previous approximation we introduced 2 slides ago, can plus beta times the test function evaluated at the embedding of the trajectory sampled at this time. So that basically means that what we're doing here is by learning, if we were to be able to learn, if we had the test functions learn, then we can use them to add an extra signal to the reward function. And that's basically what we do. And once you can do that, then you can take a gradient through it. For example, by doing policy gradients or using evolution strategies, as we described in the beginning. The story for off-policy embeddings is also similar. Okay, so where can we use this? We can use this in multiple settings. Like for example, ranging from imitation learning. So here what you want to do is minimize the distance between a policy and an expert, the one you're learning and an expert that is running demonstrations. We can use Wasserstein penalty as a trust region type of term into policy gradients. And then we can also use this for novelty search when we set the parameter beta to a positive number in the previous slide. I'll show you in a second, which is basically we're trying to add a term that encourages novel behaviors. Okay, so this is a simple example where we have 2 agents in this simple flat world. There are 2 goals. So here's, well, actually there's a single agent at every time, but the world is, there are 2 goals on like R2. And then basically what we want to do is we want to train these 2 agents simultaneously to learn the 2 different solutions for the environment. And so basically the idea here is what we said is a function, or sorry, an objective that corresponds to some of the rewards of the 2 agents plus the distance plus beta with some positive beta, and then the distance of the embeddings between them. Now for the embeddings here, what we use are the sort of mean displacement on the x-axis. So in a sense, it's cheating because that's surely going to work. But what I'm trying to get at with this slide is more like you can see here how the evolution of the test functions goes and how it is that the test functions are starting to score. They're actually kind of backwards, but they're trying to score behaviors that are different to each other and encouraging that way throughout optimization. So what happens here is the blue one starts getting, so they're backwards, sorry, so they need to be backwards. So it starts getting like a high reward for behaviors that take it to the right, while the red one at the same time is getting a high reward for behaviors that take it to the left, while also getting a reward for solving the task. So this allows these 2 agents sort of trained simultaneously to learn different solutions for the same task that achieve the same reward. Okay, so this sort of leads us to basically what I described. It leads us to what we call a behavior-guided policy gradient. So we have, again, an embedding which is given to us. Like you define the embedding, and a distance in the embedding space. And then you can use the previous technology that I described of the dual formulation to get a policy gradient algorithm. So now the idea here is that what we do is we have an alternating optimization problem where first we take a step of this sort of synchron-like algorithm for the embedding space to update the test functions using some random features, approximation of the test functions. And then we freeze the test functions and take a policy gradient step through the parameters of the policy, and then repeat and so on. So one thing you can show, this is like the standard theorem that appears in all the deep learning papers, is that under some assumptions, if you have this sort of policy improvement type of theorem, just like the RPO, if you do some kind of trust region method using a WAS distance. Yeah, but that's simple. So then the next thing is what we can do is we can use these methods. Particularly what we did is we use this with off-policy embeddings, which is, remember, we sample from the buffer of states, a bunch of states, and we use the actions that are taken there with an L1 distance. And what we show here is that this method works. So we're not really claiming that it does better than TRPO necessarily, although in these plots they do. But that if you don't put a trust region, then you do but pretty poorly. Whereas like if you put a trust region, either like a KL type of penalty or this kind of behavioral trust region, you can still solve the tasks. I mean, and in these examples, we do a little bit better than the TRPO solution. And then the next one is how to use this for sort of quote unquote novelty search type of stuff. Sorry, it's like pretty hard to read this. But another way in which you could optimize this, for these augmented rewards, the rewards now have this this extra penalty that corresponds to the test functions, is by just using an evolution strategies algorithm. And so that's the next this algorithm here, behavior guided evolution strategies. So what's there in the text is just really what I just described. We find the test functions using this alternating procedure, like the update by computing a bunch of trajectories. And then what we do, we use the test functions to augment the reward, and then take a evolution like a ES step, gradient step, you could call it gradient, on the parameters of the policy. So you can see here the example that we have here is this ant trying to solve the following task, which is you have to go around the wall to find the blue goal. But there's a deceptive reward situation here where basically the ant can go into the wall and stay there, and that's kind of a local optimum. So ideally what you want is to try to have some exploration that takes the ant around the wall so you can go to the green goal. So we see here that our method, where what we used as an embedding is the last state, promotes enough exploration by setting beta to positive to ensure that you actually end up getting to the goal. You will do a little bit better than like the NSRES in this case. Okay. And then just like a quick note, there is a recent paper by Arthur Gerten's group that builds on this work that we have, that is under submission to ICLR. So what they do here is, they use a better type of estimator for gradients when coupled with the Wasserstein distance, in case you're wondering how you can extend this. So some people have already extended that a little bit. So the next thing I want to touch on is, okay, so the next question that I mentioned I will talk about
Aldo,
Okay.
can I
Yeah.
ask one more question?
Yeah.
So, so do you have some intuition on when is the Wasserstein distance the right distance metric versus using other distance metrics? I mean, does it really depend on the problem setup
Yeah,
or?
I think it depends on the problem setting. Mostly also like here, the idea is that it would make sense if there is a meaningful distance metric that you're using in sort of the embedding space. So like so one thing I'm trying to say is this. So in the world has like an Euclidean distance, right? Like if I'm in like a 3D space, so if I can somehow leverage that distance in a more explicit sense, then I may be able to do better optimization than if I don't use the distance that exists in the world. So kind of my intuition tells me that like whenever there is a meaningful sort of distance metric that is maybe Lipschitz in some sense, across trajectories or so on, that is sort of like Lipschitz in some sense with respect to the changes in your policy, then you may be able to like get some signal that uses that knowledge of that distance that is sort of meaningful, better than like if you just use this sort of like occupancy type of measures. It's sort of like just like KL. I mean, it's only like in terms of the densities. So I think like in those cases, you may have some more explicit gains.
Okay.
Okay. Okay. So yeah. Okay. So the next one is the following question, which is how can we effectively encourage diversity in a population of reinforcement learning agents? So this is going to be on population-based training. And one thing I forgot to say is that the previous work appeared at ICML this year, and this is this year NeurIPS. So if you're also interested in this, please come to our poster this week. This is also like a talk for this. Okay, so this is also work with Jack and Christoph and Steven, his advice. Okay, so first thing is the existing methods that encourage that. So the problem here is the following. So we have a population of agents. We want to have all of these agents trained on like a single task, but try to get like different solutions for the same task, or perhaps solving the tasks better by having multiple agents trying to solve it at the same time. So some of the methods that exist, what they do is they encourage diversity by using some kind of pairwise distance between the agents, quote unquote behavior in that case. Now the problem of this kind of approach is that this may induce things like cycling or lead to some redundancy. So here is basically, so the idea is the following. If I have a bunch of points in the space and I want to like maximize their pairwise distance, one way in which I could potentially maximize it, a potential maximum is actually collapsing points into a single, single points. And then you have like the maximal diameter, the diameter becomes really large, but then all of them collapse into like a few modes. So how can we prevent this kind of mode collapsing or like collapsing of the points for a sort of diversity distance over a population of agents in this case? Question mark. So that's basically what we're going to see. So yes, as I was saying, basically also the existing methods, what they use is they use some kind of behavioral characteristic, which requires human expertise, kind of similar to the behavioral embeddings that we talked before, like in the more general sense. And the nice thing is this is actually a very exciting and area of research. Okay, again, these are the same definitions that we saw before, so I'll not linger on them. So here the approach is the following. We'll use what we call behavioral embedding, which is we sample a bunch of states from the buffer, and we look at how the policies look like on those states. The policies of the different agents. Okay, and then we use a kernel, which in this case is going to be the exponent, this kind of Gaussian type of kernel, this exponential square kernel, to compute a kernel matrix. And then we'll use the following population diversity score, which is the determinant of the kernel matrix. So this is, so this gives rise to the method that we propose, which is called diversity via determinants, or DVD. So the idea here is we have multiple agents, each of which have their own parameters, theta 1, theta 2, which we call in all together big theta t. And what we try to maximize is the individual joint reward plus a diversity type of term. The diversity term, in this case, encoded by the determinant matrix of this kernel evaluation of the pairwise, of the, I guess, pairwise kernel evaluations of the different behavioral embeddings of the policies, which are random. Okay, so why the determinant? Okay, this is a bit sketchy, but so you can show, let's just skip this one. So why to use determinants? Okay, so let me say this in like with a small example. So we have this tree where there are a bunch of states, and there are these 4 states, and then the goal is to move down the tree and going to collecting the reward at the bottom. So if you look at this tree, there are 5 optimal policies. Okay, so it's like so there are 5 optimal policies. Okay, but you can see that if we use the following embeddings for the trajectories, which are really just the actions we take, which we enumerate by -1, 0, and 1, then you see that if we use the determinant, the determinant of the 5 unique solutions is 0.9, whereas the determinant whenever we have any 2 solutions being the same is 0. That's just because being a kernel, so if you have 2 linearly dependent sort of solutions, the determinant is 0. So this is kind of, so by the way, all of this is sort of borrowed ideas or obvious facts, I guess, from the DPP literature, where you see that the determinant of this kernel matrix is basically measuring the volume spanned by the embeddings in this kernel space, so that if they're linearly dependent, if they were linearly dependent, then the volume would be 0. So what we're trying to basically encourage here is like linear independence of the embeddings in this sort of kernel space. Now what happens here, unfortunately, is that if we actually were to use the pairwise distance, then when we collapse to 2 solutions being the same, the pairwise distance is maximized. So unfortunately, that doesn't really, so if that was our score of diversity score maximizing, we wanted to maximize that diversity score, we wouldn't be able to find, on using these embeddings, of course, maybe different embeddings would be a different story, but we wouldn't be able to find all of the solutions here, whereas if we were to use the determinant, we would be able to. So that's kind of a proof by example kind of thing. And then, so then the point I'm trying to make here is that when 2 policies are the same within a population, the determinant goes to 0, but the pairwise distance may still increase. You can also run this example if you go there. Okay, and then like just a little bit more formally, so when you have small number of agents, what happens is the determinant approximation, the first order approximation of the determinant on the, using this kernel that we are using here, the square kernel, the X square kernel, basically corresponds to the pairwise distances when M, the number of agents, is like 3 or less. But then once you move to like higher order approximations, so higher order number of agents, sorry, more agents, then the higher order terms start becoming more dominant. Actually, the first order part of the approximation becomes 0. You can see this in the paper. Okay, and so for the method itself, I remember that there was a lambda t that we used to score how much diversity to add to our method or to our objective. So the idea is that we do this by being adaptive. So how do we choose how much diversity to add? We try to do this in an adaptive way. Why we do that is because sometimes you may not actually want to encourage diversity if the current solutions are very brittle. So if you're at a point where actually all of the agents should probably behave similarly because it's kind of a bottleneck, you don't want to necessarily encourage diversity that may break the current optimum and the path towards a solution. So what we do is we have a very simple Thompson sampling type of scheme to try to adapt for the lambda, which is trained by choosing, we have 3 lambdas, either 0, 0.5, or 1. And then what we do is if the score function, so the reward that we keep collecting increases for a particular choice of lambda, then we treat that as a Bernoulli sort of signal. And then we use just a simple, this very simplifying assumption that basically those signals are correct under some Thompson sampling type of sampling of which lambda to choose, based on the rewards we have gotten for those lambdas, given by the 0, 1 increased in the value. Some of these sort of ad hoc but interesting approaches of using these kind of bandit type flavored things in deep RL exist already. For example, there's another paper we have in ICML, also with these collaborators, which uses an exponential weights penalty for adapting some hyperparameters. And then there's Agent 56 that uses some adaptive scheme also for some of the hyperparameter choices. So the first the first algorithm that we use here is just using the evolution strategies type of rule. So we have all these agents, and we want to maximize their joint rewards plus the diversity term, all of which we can compute at every step. The diversity term is not unbiased, but I mean, make that approximation. And then we just take these gradients with respect to the whole population as a whole. So one nice thing about the gradient of the whole population is that, as opposed to sort of taking gradients of each agent with respect to everyone else frozen, these gradients are like kind of, so it's kind of in a single step, everyone together moves. So avoiding a little bit of this kind of potential greedy situation where like a gradient for one agent takes you this way, while the other one sort of takes you the other way, and then they go back sort of in the next iteration. Some kind of unstable cycle there, potentially preventing those kind of problems. Okay, so these are some results. So we do the same thing, but for this deceptive reward environment, we use the same. Now we use the same kind of embedding for the NSR approach, and we see that our method does better in this problem. Now for the second set of plots, what we did is we have this environment where having the half cheetah environment going forward or going backward, both give you a reward. Running all the way there or running this other way, it gives you a reward. And then we can see here that basically our approach manages to learn, if you have 2 agents, manages to learn both solutions, whereas like the other approaches sort of get stuck with 2 agents for the same solution. So this basically tells you that this kind of penalty does allow you to learn multiple solutions for the same problem at the same time. Okay, and then, okay, so do we need to adapt? That's kind of the question. Do we need to do this lambda being adaptive? So here we have some evaluations, some studies on our algorithm with a fixed lambda of 0.5 versus the adaptive version of it. And you see that being adaptive does help. So at some point you do want to sort of turn off the diversity or turn it up. And then the last algorithm is this DVD. So we call this DVD because it's diversity via determinants. And then we also notice that you can take gradients with respect to this kernel, the log determinant of a kernel matrix, and the kernel matrix that we are using. So we can use that also to take gradients coupled with policy gradients. And here you can see that this allows us to get a humanoid to work under our approach. So here the idea is that we have multiple policies and we want to just find one solution for the task. And you see that this does better than other existing methods, that at least the ones we compared against here, just TD3 without any multiple agents of TD3 without encouraging diversity between them. So one thing I want to note here is that the lambda did move throughout optimization in a sort of non-trivial way. So that throughout optimization, it tried to do different things, like getting more diversity or less. So it was not a flat solution. And if you go to the paper, there are all the ablation studies that we did about how many states we sample for the kernel matrix and other things like that. And here are some behaviors. They admittedly don't look very different. So they're not different in very much in the perhaps things we may care about, but they're a little bit different at least. So at the end, we learn different humanoids solving the task in slightly different ways. And then the last thing I wanted to talk about, I'm not sure if I have enough time, but I'll try to do this in 3 minutes. So this is the following question. So what is the right measure of similarity between tasks? Trying to move up to the meta-learning setting. We talked about so the natural consequence, the natural next question is, how do you do the same for tasks? Or for, when you have kind of an MDP itself changes, perhaps. So this is the subject of a small, very tiny paper that was at the Lifelong ML workshop, and now this is with as well. So basically the idea here is the world is full of multimodal problems. So oftentimes you want to do meta-learning where we want to train on their set of distribution over tasks that is very rich, that may not be captured necessarily very easily by a single learner. Most of the methods that exist are sort of, lots of the methods, let's say, or at least one of the most popular one, like MAML, it's sort of based on the idea of having a single fit 8 theta parameter for basically all the tasks that you may want to learn. So here what we are trying to think about is what if instead we use multiple learners instead, and how to do this. So here, how it's done right now is we have one learner to rule them all. And what we're trying to propose here is a way to instead divide the task space and use multiple learners to learn multiple, so subsets of the tasks. Okay. So also, humans interact with the world as multitask. Like that's very, very rich. So that's our motivation for trying to do this. So the idea of the algorithm is the following. So we have, train tasks, which we embed using some embedding kind of function into this sort of embedding space that summarizes the task by passing, and we construct this embedding by using what we call a probe policy. Another idea is basically using these embeddings and a metric distance in this embedding space, we can cluster all of these tasks into a bunch of different clusters of related tasks using a distance in embedding space. And then this is all like in an unsupervised way, so we don't give the clusters in advance, just the probe policy and the way to construct a probe policy and the embedding distance, the embedding space. And then the idea is that using these different clusters, you train a meta learner for each of the clusters in the embedding space for the different train tasks. And at test time, what you do is you look at your test policy, your test task. You use the probe policy to figure which cluster or which meta learner to use, and then you adapt using that meta learner. Now the question, of course, comes like, how do we capture or embed these different tasks in an appropriate way? So one thing that we can try here, so one component of that to answer that question is the probe policy. What kind of probe policies can we use? We try different things. One is a random network, and then another one is, for example, using the Perl, in the Perl algorithm, the latent variable that Perl produces as an embedding. So we tried other things as well. So, and then like how do we construct this embedding in the task embedding space? So we tried a few things. So I'll show you plots in a second. So one is using this reward-weighted feature information matrix, and then another one is this kind of next state type of embedding, and the correlated contexts with a random embedding network or like a small mammal trained on all the tasks kind of probe policy. And then we tried this kind of environments where we have half cheetah going forward, backward, and walker going forward, backward. So these are our multi-model tasks. And then you see here that these embeddings do capture, some of these embeddings do coupled with the probe networks that I described, or probe policies that I described, do capture the different clusters of the task, which are like the cheetah and the walker type of tasks. And then here you see that if you use this unsupervised type of clustering type of thing, where now you have two meta learners for each cluster, you can basically do as the Oracle would do in this very simple type of task. So it's kind of like a very work in progress type of thing. And that's it. So I mean, basically what I wanted to get at is that, so what we did here is we learn, so we asked the question how to learn, how to measure similarities between policies, how to translate that question into the task level, not answered fully at all yet, but I'll start. And then for future work, interesting things like learning embeddings, as you described here, that will be a very interesting thing. How do we learn them? How do we meta learn them? In the case of the DVD, how many agents to use for the population? And then something that I would find very interesting is to see if this kind of notion of distances or embeddings can be used to say something about transfer learning, meta learning, really actually in the context of reinforcement learning, in the way in which there was some work has come about that explores questions about transfer learning and supervised learning using Wasserstein distances, and then using determinants in other like diversity inducing objectives in other problems would be also interesting. And you can see some code there. And yeah, thank you for your time.
Well, let's thank Aldo for the talk.
Sorry, I think I went over time.
I think we have a few minutes for any questions if someone has questions.
How do you encode tasks? How do you represent them so that you can close through them?
Yeah, so what we use there, because I went very fast, sorry, was is the following. So we tried with the following types of task embeddings. So we use the probe policy, which was, for example, a random network. That's the easiest one. Or you train a meta learner over the whole train task distribution, which is multimodal. And then you use that probe policy to compute something like a Fisher matrix type of object.
Thank you.
And that's it. Yeah.
Yes, well, one question in the first part of the talk, when you have this regularization, do you have any sense how that changes the landscape? Does it become easier in maybe empirically?
No, so it becomes a bit harder because what ends up happening, so what ends up happening is like now we have an alternating problem, optimization problem. So basically these test functions, you need to update them. So every few steps or something, for example. So that's like a component that is sort of hold fixed, while then you take gradients to the other one, and then you have to update them again. So that's a little bit of a limitation. It'd be nice if that was not needed. It may be possible, but yeah. So some of it becomes a little bit brittle, but these other people that already developed this other algorithm that's based on ours seem to have had a good time. So, and they persevered and made it work. So I suspect like there are ways to mitigate this.
So one question on diversity, it seems like diversity is in the eyes of the beholder, right? I mean,
right.
So how do you kind of include the kind of diversity that we think is diverse? Like by we, I mean humans. Right?
Yeah, so yes, I mean right now that's not clear how. Like so ideally maybe what you would want is somehow to pick the right embedding, right? So the problem here is precisely that the embedding itself is like arbitrarily picked as you just want a bunch of states in the past, and then you want to be different on those states. So what's happening right now is we sample a bunch of states, and then you want all the policies to kind of behave slightly different on those states. So if you could figure by, for example, having a human label things like, okay, this was actually different in a sort of meaningful sense, maybe you can start coming up with ways of selecting which things would a human beholder would consider actually different. But I think maybe this would require human supervision in some level at least. But could be something like you actually have some labeler that tells you, okay, that was actually different. Because what you need is you need to figure what the right dimensions of diversity are. And that seems hard to know without having any supervision of what you care about. You know? Like,
yeah. Cool. Well, I guess we are 6 minutes past 5. So let's thank Aldo once more.
Thank you.
And I guess, Aldo, you have a bunch of meetings scheduled.
Yeah,
So,
tomorrow, no?
Yeah, so I think you have, it was recently added, you have one meeting today, and I will like ensure that that will go on smoothly. And then I think you have like bunch of like meetings tomorrow, and you also have like break in between so that, you know, you also have like some time off. But yeah, like,
Perfect.
cool. So yeah, I'm happy to, you know, like take you to the, you know, like the other Zoom call. But yeah, it was really nice, you know, like hearing you talk. And
Thank you. Yeah, it was great.
yeah, cool.
Thanks.
I hope. Okay.
What should we do? I should just...
Yeah, I'll just, yeah, just like go to the other Zoom, I'll be there.